going to draw a three-dimensional. Okay, so when I draw a cube like that, it's meant to be rotated so that the dashed lines, you can't actually see where those things are. Does that kind of make sense? Like what I put there? Recording? Alright, I'll keep it appropriate. Yeah? You ready? What are you up to?
Hey, how many textbooks do you have?
For Chem?
Yeah.
3. Okay, so in this one, we're looking at 1, 2, 3, 4 as being 1, 2, 3, and 4. And then can't see 5, 6, 7, and 8 being 5, 6, 7, and 8. So that's our corner pieces. And then in between each corner set is one atom at each face of the cube. One on top, one on the bottom, and then one on each side. So like this one here that's on the 2, 3, 6, and 7 cube, we'll call this atom number 5. Now, so for unit cells, what we're trying to do is we're going to try and link information that's useful to us. So essentially what we want to do is this cube, we want to be able to connect the side length of it with what the radius of the atom is. And there's two kind of key connections with that. We can use density to figure out what the volume of the cube is and from that length. And then we can figure out what the relationship is between the length of the side and the radius of each atom using just some basic, like, where things are touching one another. Okay. Now in a body-centered cubic, it's again your cube. But this time, instead of having just your 8 corners and then one in each face, you have one single atom inside of the cube, completely isolated from all of the walls. Okay, so that's this one here. This is your central cube. The other 8 in this are your 4 on top and 4 on the bottom are your corners of your cube. Okay. Now the big thing that you need to be able to understand at the top end level of this is just which atoms are touching, and then how can you do trigonometry from that. So in this one, for the face centered, when you have a corner, a face, and then the opposite corner on that side, those 3 atoms will touch. So in other words, there's a gap between 3 and 7 here, there's a gap between 6 and 7, but from 2 to 5 to 7, those are all in contact. So what we can say is, we can say that there's the radius of this, 2 radiuses of 5, and a radius of 7 is the same thing as your diagonal across your face. And from trig, we can do some trig on that to figure out what the relationship is between R and L. So if I can kind of draw this triangle here, this is the length of your cube, this is the length of your cube, and this is 4R. So we have a right triangle that goes like this, 4R, L, and L. How's that sound? Fair enough? So from there, if we want to know the relationship between these, what we do is we would say, for face, switch slides here. So for face-centered cubic, we have this kind of along the side of L, L, and 4R. So what we can say is that 4R squared is equal to L squared plus L squared. And so we get 16 times R squared is equal to 2L squared, which means that R is equal to root 1 over 8 times L. And then the reverse of that, L is equal to root of 8 times R. Okay? Does that kind of make sense? So, based on the way that the atoms arrange, these are the 2 arrangements where you want to be able to do math on this. And here's what the math looks like. Okay. So here we're in a face-centered cubic arrangement. It's called FCC, face-centered cubic. So it gives us a problem where it says aluminum has this density, 2.70 grams per centimeter cubed. It says in the face-centered cubic arrangement, determine the radius of the metal in picometers. Okay. So what I would do for this is I need to figure out in that 1 unit cell, go back here. in this, how many atoms of aluminum are there total? And then from that, in this, we're going to then figure out what the radius of each atom is. Okay. So first of all, looking at this, so we have our cube. I don't know how well I can explain this, but when you're looking at a cube like this and you have an atom at the corner, that atom is not exclusive to that unit cell. So this atom here does not just belong to this unit cell, it belongs to 8. Or in other words, it's shared by a cube right here, a cube behind, and then 4 more cubes above those 4. And so each atom at the corner only contributes 1/8 of that atom to the cube. So for the 8 corner pieces total, that's like having 1 atom. So we would count 8 corners times an 8, so we get 1 atom from this. Now an atom that's on the side, that's on a face like this, how many cubes would share that atom? 2 is correct. So this one and then the one directly adjacent to it. So each of those counts for a half. And we have 6 faces to the cube. So we would get 3 atoms for all the face-centered arrangements. So total, for a face-centered cubic, you're going to have 4 atoms. Okay. So let's go back to the problem then. So we have 4 atoms, we know the density, we want to find the volume of the cube. So what we can do is we can say, okay, well what's the mass of 4 atoms? So 4 atoms of aluminum. We would take 6.02 times 10 to the 23rd atoms. Let's say that's 1 mole. And then we would say 1 mole of aluminum is 27 grams of aluminum. Okay. So we're going to work that out, and I worked this out already. We don't need to do that. So this comes out to be 1.79 times 10 to the negative 22nd grams. Okay, so let's switch colors here. So 1.79 times 10 to the negative 22nd grams, and we also know the density is 2.7 grams per centimeter cubed. So we can change that into centimeters cubed. So we can figure out that our volume of our cube is 6.64 times 10 to the negative 23rd centimeters cubed. Alright, let's pause here. So the volume of this whole cube is this volume. What would you do with this to figure out the rest?
Cube root it.
You cube root it because L cubed is your volume. So if you cube root this, that tells you the length of the side. So L is equal to the cube root of this answer, which ends up being 4.05 times 10 to the negative 8. Now your units on that are in centimeters. Okay. So really 4.05 times 10 to the minus 10th in meters. So that's our side length. So now we can plug that in for L, and we want to figure out what R is. Right? So R is going to be square root of 8 times that. This is wrong.
It's 2 times square root of 2 times that, so it's the same thing.
Oh, I want R though. Okay, I was going to say I should be dividing. So anyway, I get my radius to be 1 over, this over square root of 8, which comes out to 1.43 times 10 to the negative 8 centimeters. Okay. Now this asks for, I think, picometers. Picometers. That's 143 picometers. Which is a reasonable answer for a size of an atom. Usually an atom's going to be 100 on the low end, 200 something on the big end. So for aluminum, that makes sense. That's it. That's the style of problem for this. Now, some summary information, and then I'll show you what the Chem Olympiad question was like. When you're counting atoms, a corner piece is worth 1/8 of an atom. A face is worth 1/2. A side is worth 1/4. And something internal to the cube is worth 1, because it's not shared. Sides are shared by 4 cubes. Faces are shared by 2. Okay? So a question that came up on one of them was this one. So it said, here's a unit cell of perovskite structure. It's got 3 different types of atoms, A, B, and C illustrated below. What's the empirical formula of the substance? So for that, we would look at B, and we would say, okay, B has 8 corner pieces. So how much B do I have? Well, I have 1 for B. And then for A, I only have 1, but it's in the center. So it's not shared with anything. So I have 1 of those. And then for C, I have 1 on each side of the cube. So I've got 1, 2, 3, 4 along the top part. I've got 1, 2, 3, 4 in the middle section. And I've got 1, 2, 3, 4 at the bottom. So I've got 12 times a fourth, because each one of these is shared by 4 cubes. So I have 3 of those. So the formula for this is ABC3. Now, if you saw something, my guess is you would see something like this on a local, and then the second type of problem on the but you know, who knows? Who knows with our stuff? All right, so that's a brief introduction to unit cells. If I can summarize the 2, now that you might understand it a little bit. For body-centered cubic, for the body-centered cubic, you need to know, here's your center one. You need to know that you have 2 atoms total. And this one's a little more challenging in the trig. Your contact point is from one end of the cube to the opposite end. So like top left to bottom right. And the contact is through the central atom. So your triangle, if we will look like this. It'll be the side length on one side, a diagonal on the other, and then a diagonal across the entire cube. The diagonal across the entire cube is 4r. The one side length is L, and then the other side length is L squared plus L squared, so it's root 2 times L. So when you end up working this out, R ends up being equal to root 3 over 16 times L, and L is root 16 over 3 times R. Right. I don't want you to memorize that, but like hopefully you recognize that. Like I did this and I screwed up and I put square root of 2 squared and I put 4 L squared, ended up with 5, 16 over 5. So anyway, and then for the face center cubic, you're going to have 4 atoms, and your diagonal is going to be along the face. Okay, that's about it. Okay, cool. Let's stop doing that. So next on our agenda, logistics. So who does not have a ride? Who can you go with? You want the Kosh? You need to like find a ride with someone. I guess we'll solve that later. I was hoping something like,
we just solved that.
oh, okay,
Literally
cool.
just solved in my mind.
Perfect. Does everyone know where they're going?
U of M Dearborn, right?
Yeah.
So which like area of it?
Okay, so when you're driving along to U of M Dearborn, yeah, so you're going to turn on Evergreen from Michigan Avenue? Probably. Don't you guys have like those things though? You guys have the GPS stuff? Yeah, I don't have that. Anyway, so here's Michigan Avenue, and then Evergreen is your entrance to like where the mall is. So the mall is up here on the right from Evergreen, and then U of M Dearborn starts a little ways past that. Whoa. So you're gonna come like past a couple turnarounds. If you turn too early, as long as you can get into the parking lot, you're fine. I usually turn at this one because I lose my nerves that I'm gonna miss a turnaround. So anyway, there's gonna be a whole bunch of parking lots, and you're gonna go past them until you run to a dead end and you can only turn left. And then there's a big parking lot up there, and we're looking at a building over here. It's kind of like circular.
I'll send out a map.
So anyway, it's the SSB, Social Sciences Building,
Social science.
which you think they would do it in a sciences building, but they don't. So it's got one of those big like amphitheater type lecture halls in it, so that's why it looks kind of circular. So anyway, yep. Timing wise, you want to get there well before 4:30 because otherwise you might like show up like Zane and nobody knows you're there. But get there. Most kids get there around 4. Bring calculator. Bring something to write with. I think that's all you need, right? So you'll sign in when you get there. They'll get you your test, and they start at 4:30. When you're done, you're done. You can leave. And then cool. That's it. I'm gonna probably stay there the whole time. So when you guys are taking your test, I meet with the other chemistry teachers and we talk about some things. And then as long as I'm cleared for this, my plan is to stay there. And I'm gonna go drive over to the mall and have dinner there. So, and I'm gonna wait for them to announce the scores at 8. So if you don't want to stay for that, it's fine. But if you want me to send you a message, you can leave me like a number or Twitter or something, and I'll send you like who got into where. Are you recording all this? It's fine. Anyway, I haven't said anything wrong. And then if you want to stay, if there's only a few of you, I might buy dinner. So, okay, cool. Those are logistics. All right, now we need to talk about tiebreaker. You got this?
Yeah.
All right.